At this point, the only genuine vector space that we have encountered is Rn, right? Rn is a vector space. It satisfies all these properties. I guess I should say that any subspace of Rn is also a vector space because, right, automatically the operations will satisfy these properties. The only question for a subspace is it closed under addition and scalar multiplication? And that's part of the definition of a subspace, that it be closed. So Rn and its subspaces are really the only vector spaces that we've encountered so far. But there are a few other subspaces worth talking about. So one is the matrices of some given size, so say m by n. So if you think about all of the matrices of any given size, say 2 by 3, it seems plausible that they form a vector space because the only difference between matrices of this size and vectors in R6 is what shape these entries make, right? For this matrix, 2 by 3, there are 6 entries, but they're in this rectangle. In R6, there are 6 entries, but they're in a column. So it kind of makes sense that the shape that the entries make isn't so important, or doesn't affect whether it's a vector space or not. So it seems plausible that the matrices of a given size should form a vector space. And let's just check. So to form a vector space, we have to have a collection of vectors, which, well, if we're going to say that our set is all matrices of a given size, well, that's a collection of vectors. And we have a choice of scalars because we're going to use the real numbers. I guess we should say that our matrices have real entries. Okay, so now we need an addition operation and a scalar multiplication operation. But for matrices, we already have an addition operation. You just add component-wise, or add matrices entry-wise. For that to be defined, the matrices that you're adding have to have the same size. But remember, if we're pulling matrices from just one of these spaces, it will always have the same size because we're fixing m and n, right? So, and then scalar multiplication also happens entry-wise. So we already have operations addition and scalar multiplication. So if you add two matrices of a given size, you get a matrix of the same size. So it's this set, matrices of size mn, is closed under addition. We already know matrix addition is commutative and associative, so there's nothing really to check there. We know that there is an additive identity. Remember, an additive identity is really just something that counts as 0. And for matrices of a given size, the matrix of all zeros is an additive identity, right? If we added anything to the 0 matrix, we get whatever we started with. And also, there are additive inverses because the additive inverse for A is a matrix negative A, right? Because if you add A and negative A, you get the 0 matrix. So we have additive inverses as well. So all of these things are satisfied. What about for scalar multiplication? Well, if you multiply a matrix of some size by a scalar, you get a matrix of the same size. So, multiplying by scalars keeps you in the same matrix space, so that's closure. We do already know that scalar multiplication is associative, and multiplying a matrix by the scalar 1 does give you the same matrix back. So the scalar identity, multiplying by the scalar 1 does give you the same matrix back. Okay. And then finally, we already know that scalar multiplication distributes over matrix addition, so nothing to check there. So that means that the collection of matrices of a given size forms a vector space. Okay. Great. So that's one vector space that we've actually encountered, but we've never really described it as a vector space. Now you might wonder, what is the advantage of knowing that it's a vector space? What we'll see is that all of the tools that we have for linear algebra, that is things like span and bases and linear combinations and dimension, all of those things will apply just as well to this vector space as a Euclidean vector space. So that's why we want to identify things that are vector spaces, because then we can use all of our linear algebra tools on those vector spaces, even though they aren't Euclidean vector spaces. All right, let's look for other possible vector spaces. How about the collection of all polynomials of a given degree? So some people use a sort of a blackboard bold P with this double vertical line to denote the polynomials. I'm not going to do that because usually that double blackboard bold P means something different for a lot of mathematicians. So I'm just going to use a regular P instead. All right, so to check if this, right, we should suspect that this forms a vector space because, right, we already have an addition for polynomials and a scalar multiplication, and since those addition and multiplication are built out of the addition and multiplication for real numbers, they already will distribute and be associative and all those things. So it seems plausible that this will turn out to be a vector space. So let's check. So we need a collection of vectors. Well, yes, that's the collection of all polynomials of degree n. We're fixing n here. So for this to form a vector space, or to have a hope of this forming a vector space, you have to choose n ahead of time and stick to your choice. Of course, different choices of n will give you different vector spaces, but that's fine. Okay, so we need a collection of vectors, which we have, right? Polynomials of a given degree. We need a choice of scalars, but that's just going to be the real numbers. We have addition and scalar multiplication operations already, because if you have two polynomials, you can add them. And if you have a polynomial and a real number, you can multiply them. So we already have these operations. All right, so what about closure under addition? If you have two polynomials of degree n and you add them, do you get a polynomial of degree n? Well, actually there's a problem there because, well, I mean, what if we chose n equals 2? Right, that means we want polynomials of degree 2. Well, here's a polynomial of degree 2. Here's another polynomial of degree 2. If we add these two things, do we get a polynomial of degree 2? No, we get a polynomial of degree 1. So actually this collection of polynomials is not a vector space because it doesn't satisfy closure under addition. So we can't just take the polynomials of degree n. You can see what happened here is because these leading terms canceled, that's what made the degree smaller. So maybe what we should do instead is let p sub n be the polynomials of degree, I can't spell degree less than or equal to n. Okay. Well, if you take any polynomials of degree less than or equal to n and you add them together, you do get a polynomial of degree less than or equal to n, right? This now is no longer a counterexample because our sum polynomial over here has degree 1, and 1 is less than 2, so right, we're okay here. All right, so that takes care of the closure issue, right? So commutativity of addition. Well, addition of polynomials is it's built out of real addition, and that's already commutative and associative. Is there an additive identity polynomial? Yes, just the zero polynomial. This is another reason why we have to, we can't take just polynomials of degree n. It's because the polynomial that you need for an additive identity is the zero polynomial, but the degree of the zero polynomial is 0, and so it doesn't really, so we wouldn't have an additive identity if we stuck with only degree n. So we need polynomials of degree less than or equal to n so that we have a 0 in our vector space. Okay, so the 0 polynomial is our additive identity, and there are inverses because there's a negative for each polynomial. And scalar multiplication is built out of real multiplication, so it's closed under scalar addition, or I'm sorry, we're closed under scalar multiplication, and it's associative. And multiplying a polynomial by 1 gives you the same polynomial back, so we have that scalar identity property. And since addition and multiplication are really just real addition and multiplication in disguise, we already know that they distribute. So this means that this collection of polynomials is a vector space. Notice that, so for every n, we get a vector space P sub n, but if we took all polynomials, that would also satisfy all of these properties. So this is also a vector space. This vector space of all polynomials, of course, it's much bigger than the individual polynomial vector spaces P sub n. Really, the difference between them is that this space of all polynomials is actually infinite dimensional, which is something that we haven't really encountered before. All right, one last example of other vector spaces. Suppose that we have some set S, could be anything, could be an interval in the real numbers, it could be just a set of discrete points, and let's let S to the R be the collection of functions from S to R. So this notation is a little funny, don't worry about why that notation is good notation. It turns out it is good notation, but that's not important. So this is the collection of functions whose domain is S and whose range is R. Okay, so this is a set. The reason we might expect this to form a vector space is because we can define the sum of two functions using the formula, right? The sum of f and g is f of s plus g of s. That defines an addition on functions. And we can define a scalar multiplication on functions this way. So the scalar a times the function f is a times f evaluated at s. So this is for a little s in big S, right? Same thing up here for a little s in big S. So what's happening here, sort of the term of art to describe what is happening here, is that we're using the addition and multiplication in the real numbers to define addition and multiplication of functions pointwise. So this definition, these are pointwise definitions. All right, so we have these operations, which means, well, an addition and a scalar multiplication, that makes it seem like this might be a vector space. So let's check. So we have a collection of vectors, we have a choice of scalars. The scalars are just the real numbers again. We have an addition and a scalar multiplication. Is it closed under addition? Well, if you add two functions, you get a function, so yes, definitely closed. Is addition commutative? Well, it's automatically commutative because addition for functions is defined in terms of addition for real numbers, but addition for real numbers is commutative, so we get commutativity for free, same for associativity. What about the existence of an additive identity? Well, we would need a function that I guess we would call the zero function, and you can probably guess how to define it. If you evaluate the zero function at any element little s in big S, what should that be? Well, probably 0, right? So with this definition, if we take any function and add the zero function, is that the original function? Well, we can check. Right? Take this sum, evaluate at little s, so here little s is in big S. What is that? Well, by definition, that's f of s plus 0 of s, but 0 of s is 0, and f of s plus 0 is f of s. So we're done, because right, this means that f of f plus 0 is equal to f, right? Because they're equal pointwise, right? Functions are equal if they're equal pointwise. So f plus 0 is equal to f, and that means we have an additive identity. Similarly, negative f is just the function, so how do I want to write it? The function negative, the additive inverse of a function f is the function that when you evaluate it at little s, you get the negative of f of s. So no big surprise there. That gives us additive inverses. Scalar multiplication, because scalar multiplication is defined pointwise right here, we get all of the nice properties for scalar multiplication for free because they all come from scalar multiplication in real numbers. And distribution we also get for free because we're really using pointwise operations in the real numbers. So this collection of functions is also a vector space. In fact, there are lots of variations on vector spaces of functions. So some of them are, say, sure, we can write it this way. So this C of R, this is the usual notation for continuous functions from R to R. We could ask that our functions be differentiable, and the way to say that is to put a superscript here. So this is a 1, it's not a prime. Right? So this is also a vector space. This is functions from R to R with continuous derivatives, right? And so on. You know, you can insist that there be continuous derivatives of any order. So of order n. So you can see there are lots of subspaces of function spaces that are also vector spaces. So even though this list of properties that vector spaces have to satisfy, even though this list is very long, it's actually not uncommon to have some collection of things that forms a vector space. Because most operations, most addition and multiplication operations, most addition and scalar multiplication operations that you would ever define are going to satisfy most of these properties. So lots of things are vector spaces, and that means we'll be able to apply our vector space or our linear algebra tools to lots of different situations whenever we have a vector space.